Hi there, and welcome back to Basic Math for Economics. In this video, we're going to move on to our final unit of this little boot camp right here, and we're going to start talking about optimization, which again is one of those things that you're going to do a lot of in economics. So let's start off by talking about unconstrained optimization, and just with a single variable. We'll warm up, we'll get to the harder stuff later on. So anyways, like I was saying before, optimization is a frequently relied on tool in dealing either in microeconomics or macroeconomics. We're going to maximize profits, we're going to minimize costs, we're going to maximize utility, we're going to minimize expenditures. We're going to do a lot of things that require any kind of optimization technique. And really, whenever you hear that somebody wants to maximize or minimize something, they're talking about optimization. So we can actually break down our optimization into two different types. So the first type, which we're going to talk about here, is unconstrained optimizations. And that's just where we want to maximize or minimize one variable or more. We can have several variables, but there's no restrictions on what kind of values that they can take. This is going to be something like a profit function. You know, the monopolist can choose whatever value of quantity that they want. The price is going to be determined by that quantity, but there's no restriction. It doesn't have to meet some kind of certain parameter other than satisfying the demand function. On the other hand, we have constrained optimization. These are situations where we want to maximize variables of interest. You know, we want to maximize certain things, but we have limits on what kind of values that these variables can take. So these are going to be things like budget constraints. This is going to be things like a production function. These are going to be very significant things that change what we can do with our optimization problem. And we have to consider those constraints when we do our maximization, because it could cause us to get to a different solution. Anyways, I want to start by reviewing unconstrained optimization, and we can do that by looking at a profit maximization function. So let's just set this up right here. So let's suppose we had a monopolist serving a market, and the monopolist faces an inverse demand function of price equals 250 minus 2 quantity. Now, notice that I'm using an inverse demand function here. I'm doing that purely for convenience. It makes the math a lot easier to work with an inverse demand function. We could do this with a demand function if we wanted to and get the exact same answer. We just need to be careful about where we're putting in our quantity. But anyways, at the same time, the monopolist is also going to face a constant marginal cost of production of C equals 50. So my question is, what value of Q maximizes the monopolist's profits? What is the corresponding price and profit level? This is a very common problem you will be asked to solve in economics. So let's work through it. So if I wanted to skip this and go back to, what we know about a monopolist is just going to set their marginal revenue equal to their marginal cost. We already discussed how to do that, and we can figure our optimal quantity that way. Yes, it's one way to do it, but I want to set this up using the optimization technique. The reason why I like this technique, and I actually prefer it in my own work, is because it doesn't require me to remember all of these rules. In fact, I could not remember that marginal revenue equals marginal cost in equilibrium, and using the optimization technique, I'm still going to get to the same answer. So it's great if you don't like remembering things like marginal rate of substitution equals marginal rate of transformation. If we understand how to optimize correctly, all of these rules are worked in. In fact, the rules are derived from this optimization technique. Okay, so setting up this problem, we need to have a few elements, and these are steps you want to think about when you're setting it up. So the first step, we need to define the problem. Now, it's as simple as saying this is a maximization problem. We could have a minimization problem, but in this case, we are maximizing. So I'm going to start by writing that. We are maximizing. The second thing we need to do is we need to define our choice variables. And these are the variables that we are able to choose naturally, and they're the variables we're optimizing for. So in this case, we only have a single variable, which is our quantity. We are choosing the quantity that maximizes our profits. So what I do is I write all of my choice variables underneath what my problem is. So we are maximizing for Q. Now the last thing we need to do is we need to list our objective function. This is our goal. This is what we are maximizing. So in this case, we are maximizing profits. So there's my whole problem right there. I am maximizing for Q my profits. But we can better define this, right? We don't want to just leave that as pi for profit. Well, I know that profit is equal to my total revenue minus my total cost. So I can substitute that in there. So now I'm maximizing Q, my total revenue minus my total cost. But I can even expand upon that more. So I know that my total revenue is my price times my quantity, and I can substitute in the inverse demand function for P, and I know that my total cost is 50 times Q, and that's just because I have a constant marginal cost. So I can substitute in for total revenue and total cost and get a function that is just a function of Q, which is exactly what I'm looking for right here. Of 250 minus 2Q, all that times Q, minus 50Q. And we are going to maximize that for Q. Well, there we go. That's a problem we can work with, and that's something we can figure out. Well, once we get to this point, we have a properly defined problem, we have everything that we need, we're ready to calculate our first and second order conditions, and second order if need be. We don't always need to calculate those. You're going to get a good sense of when you want to use a second order condition. But anyways, to calculate a first order condition, that's just a simple derivative. But before we do that, I want to point out that it's really important to get a good sense of how to set up problems this way, because it's going to keep the problem organized, it's going to prevent you from making mistakes, and if you have a situation where you just can't remember an equilibrium rule, this optimization technique is going to take care of that rule for you. All of the rules are essentially baked into these problems. So that's my tip for you. When you're facing any kind of optimization problem, set it up like this first. Make sure you list all the variables of interest that you're maximizing for, all of your choice variables, and make sure you properly define your objective function. All right, now let's go back to first order conditions. So to calculate a first order condition, all we're going to do is take the derivative of the objective function for each of our choice variables. Now we only have one choice variable here, so we're only going to have one first order condition. If I had 2 or 3 choice variables, I would need a first order condition for each one. But anyways, we calculate our derivative of the objective function, and then we set it equal to 0. Because if you remember, when we take a first derivative of a function and set it equal to 0, that's where we get either a maximum or a minimum. Remember, we don't know which one we have, but setting it equal to 0 will guarantee to give us one of those points. So let's do that. Now, again, we only have one choice variable, quantity in this case, so I'm going to take the derivative of my profit function with respect to quantity, and I'm going to do this real quick since we've practiced derivatives already. We're going to get 250 minus 4Q minus 50, and then we set it equal to 0 because that's where a maximum happens. Well, that's just an easy equation right there. That's one equation and one unknown, so we can solve that. And before we do that, though, just take a look. This is actually the same condition as marginal revenue equals marginal cost, because those first 2 terms there, 200 minus 4Q, that's actually just my marginal revenue. And that last term, that's just my marginal cost. So that's fantastic. That's why I was saying that that rule is completely baked into this optimization technique. We don't need to remember it if we know how to optimize. So anyways, like I was saying, this is just a situation with one equation, one unknown, and I can just solve that. So let's solve this for Q. Well, I can combine the 250 and the minus 50 to get 200. I can move the 4Q to the other side, and I get 4Q equals 200. Dividing both sides by 4, I get my equilibrium quantity. Q star equals 50 in this case. And that's it. And if I wanted to, I could go back and I could calculate, like I move my head a little bit, my equilibrium price and profit level from that information. We'll do that in just a moment. But before we do that, I want to actually make sure that this value of Q actually maximizes our objective function. So let's check that first. So remember that when we set it equal to 0, our first order condition, we have either a maximum or a minimum, but we don't know for sure which one that we have. In order to tell that we actually have a maximum, we need to look at the second order condition, or the second derivative of our objective function, and that derivative needs to be negative. So let's take a look at that. Let's differentiate this with respect to Q again. Well, if I do that, it just equals a constant. In fact, it equals negative 4, which we know for sure is always going to be negative, and that confirms that we have a maximum. Since our second derivative is negative for every possible value that Q could take, we're dealing with a maximum in this situation. So that's good to know. We know that we have correctly maximized rather than minimized this problem. All right, last step. Let's calculate our equilibrium price and profit level. Well, this is actually really easy. All I need to do to get the price is plug back this value of quantity back into my inverse demand function. So I plug in 50 for Q, and I get my equilibrium price is 250 minus 2 times 50, or 150 in this case. And then I plug Q back into my profit function as well, and I get my profits. Or I could just do price times quantity minus cost times quantity. That works just fine. But plugging all that back in there, I'm going to find that we're going to have a profit level of 5,000 right here. And that's it. That is an entire problem where we have optimized, unconstrained optimization for a single variable. And that's actually all for this video. Thanks for watching.